I will begin with a word of prayer. Dearly Father, we thank you for this day. Again, I thank you for this class and this time we have to study your creation. Help us to glorify you, what we do, Lord, and to understand a little bit more about linear algebra today, Lord. In your name I pray, Lord Jesus. Amen. So first, a word of warning. I think the homework, I would advise, I believe, a good course of action would probably be to do problem 80, let's see here. I'm thinking, what in the world was that? Advice, do problem 87, then do problem 86. The other piece of advice I have is I forgot to tell you SO3 is equal to R in R3 by 3, such that R transpose R is equal to the identity and the determinant of R is equal to 1. That's kind of important for that problem, I believe. So, yeah. Beyond that, I would just tell you for problem 87 and 86, you should remember the theorems we have about, we can complexify a transformation, we can complexify a matrix, and as such, things about like the complex eigenvalues of R, you should probably be thinking about that. The determinant is the product of the eigenvalues is important for that problem. But that's all I got to say for now. Yeah. So we're now I'm going to start in section 10.3 of my 2016 notes, and I there talk about bilinear forms.
Why don't you have that chapter in your notes this year?
I don't know. It's a good question. I probably should, right? So I think the answer to that is related to remodeling my basement. So.
We should just copy paste the whole thing.
Well, yeah, but I have changed significant aspects of the course, so it's not quite that easy. But yeah, that's basically what I'm doing at the moment is copy paste. So chunk. So I do think reading sections 10.1 and 10.2 might be helpful to you guys for the purpose of like studying for the final, because there I talk about dual spaces and quotient spaces, and it might be useful for you just to look through it. I don't know. I could be wrong. Okay, here's the definition. So let U, V, and W be vector spaces over F. Then be a mapping from the Cartesian product of V and W to U. I'm sorry. This is an if, not then. What's wrong with me? If this is a function for which, let me just stupid thing. Number 1, b of say cx 1 plus x2 comma y is equal to c b of x1 comma y plus b of x2 comma y for all x1, x2 in V, y in W. And 2, b of x comma cy1 plus y2 is equal to c b of x comma y1 plus b of x comma y2 for all x in v and y1 and y2 in w, then b is an element of the bilinear forms on v cross w that take their values in u. In other words, b is a u-valued bilinear form on v cross w, if you want some language for it. All right. Further, we'd also say this: b is an element of like just the bilinear forms on v. If b was an element of the bilinear forms that go from v cross v to the field. So a lot of times when people talk about bilinear forms, they're talking about scalar valued bilinear forms, right? But I wanted to give you the definition, or at least the possibility that it's vector valued. So, theorem. The set of bilinear forms from v cross w to u forms a vector space with respect to the usual pointwise operations on functions, right? In other words, you can say that this is a particular subspace of the function space from v cross w to u, right? Remember that giant concept we had at the start of the course, like function space, right? Set of functions from one set to another. Supposing that the codomain of the functions allows for addition, we can define addition of functions pointwise. We can define scalar multiplication of functions pointwise, and that gives us this giant vector space. Well, this is a subspace of that, right? These are very special functions that have this bilinearity. And you can prove that if you take the sum of two bilinear functions, you get another bilinear function. And if you take the scalar multiple of a bilinear function, you get a bilinear function, right? But this is something new, right? Before this, we've studied linear transformations, right? They just have one input. Now these have two inputs, yeah? And each one is linear. So that's what we're looking at here for the moment. So let's look at an example, yeah? Okay, so we could define b of x comma y equal to x transpose m y for x in, let's say, fm and y in fn, given M, what kind of matrix? What's that? M by n? Yeah, I think that's right. Yeah. So what is this? This defines B an element of the bilinear maps from, let's see, in this case, Fm cross Fn, and the output is a scalar. So this gives you tons of examples. Any matrix like this, you can make a bilinear form like that. Yeah?
So for a real vector space, would the inner product be a bilinear form?
Yes. Yeah, for a real vector space, The inner product is an example of a bilinear form. In fact, that's going to be one of our major applications of this whole discussion. Very good, yeah. For complex case, the conjugate linearity, the other thing ruins things. But good news, folks, we're going to keep it real from this point in the course, at least for the next couple of lectures, yeah. So, all right, so that's example one. Example two, we can define a bilinear form that goes from n by n matrices across n by n matrices. And the output is, again, an n by n matrix, okay, by b of x comma y equal to, with, oh, interesting, I do x m y plus yx. That's funny. So you can, we can check on the bilinearity of this, right? I'll do one of them. Which guys do you want, the first or the second slot? Second slot, all right. So let's look at b of x, and we'll do cy1 plus y2. By definition, that is x. Now M is a matrix that's given here, by the way, guys. So like, and I think it better be a square matrix, right? Some square matrix. Then this is the definition. So I have xm, and then I put cy1 plus y2 plus cy1 plus y2 times x. And then we just, use properties of matrix multiplication. Pull the constant out. And we got ourselves an xm y1 plus y1x, and then plus x m y2 plus y2x. Lo and behold, that is c b of x comma y1 plus b of x comma y2. So there you have it. That is a bilinear form. I have another example. This one's slightly more important, actually. So let's consider v equal to the span of beta. As usual, beta is v1, vn, right? And we'll form v dual, the dual space, right? So that we know the story. It's the span of beta dual, right? We proved this before. So, yeah. So, if alpha and beta are in V dual, and actually, I'm sorry I even talked about the basis. I'm not even really going to do anything with it right away. Okay? Sorry about that. But suppose you've got dual vectors, alpha and beta. Yep.
Is beta your basis?
Ah, rats. Gamma. Alpha and gamma in V dual. Yeah, my bad. Sorry, run out of letters. Then define alpha tensor gamma as a mapping from V cross V. Well, I said we're keeping it real, so to the reals. Right. Let it be understood, all vector spaces over the reals. All right. I was still doing some homage. I mean, I threw an F over there, but in my heart, it's it's real. Of course, a lot of this could be done over other fields, but anyway. So how do we define this? Well, here's how it goes. Alpha tensor gamma, let it act on a pair xy. What's the formula? Well, the formula is simply alpha of x, gamma of y. That's the definition, right? And I'm arguing that, in fact, that makes my claim alpha tensor gamma is in fact an element of the, the bilinear forms on V dual. In other words, it takes in a pair of vectors. Oh man, that's V, isn't it? In my notation, isn't it? Yeah, V, not V dual. Sorry, guys. Let me get this straight. In other words, it's a bilinear map from V cross V to the reals. Let's prove it. It's not hard. So we got alpha tensor gamma on like cx1 plus x2 comma y. What happens here? We have alpha of cx1 plus x2 times gamma of y, and that's c alpha of x1 gamma of y plus alpha of x2 gamma of y, which is c alpha tensor gamma acting on x1 comma y plus alpha tensor gamma of x2 comma y. Therefore, we have linearity in the first slot. Do I need to write down the other one, or do you guys see it? Like, we can easily check the same result for alpha tensor gamma acting on x comma c y1 plus y2, right? It's fairly evident by it's almost the same calculation that this is going to give me c alpha tensor gamma acting on the pair x comma y1 plus c plus alpha tensor gamma acting on x comma y2. So we have linearity in both slots. There you go. This is a way we can build bilinear forms from dual vectors. See this? We can build bilinear forms from dual vectors. It then becomes a somewhat interesting question, like, given a bilinear form, is it just the tensor product of a couple dual vectors? And the answer is sometimes, but not always. So anyway, now I think if you can do this for 2, you probably can do it for 3, right? So you could take the tensor product, like, we haven't even defined a trilinear form yet, but like, you guys tell me, what would I do if I wanted to define, say, alpha tensor gamma tensor sigma, and I wanted to define something on a triple? How would that be defined? Supposing that alpha, gamma, and sigma are on the dual, all duals. There you go. Indeed, and this would in fact define a trilinear map on V cross V cross V. So it turns out we can actually build multilinear maps from this trick. let's go on here. What on earth? What kind of... Is that even a dry erase marker? Like, what is that? All right, good. Top hat code, no less. Ah, the lowest use of a whiteboard.
You've used a whiteboard for top hat code before.
What's that?
You've used a whiteboard for top hat code.
I know, but I mean, I don't like whiteboards, but it's almost dishonoring to a whiteboard to use it that way. I mean, almost. So, I'll shut up. Proposition 10.3.5. Okay, so here I have, let's say U is the span of gamma. V, I think, is going to be the span of beta. W is the span of... Oh, no, this one was wrong. My bad. W is the span of gamma. U is the span of upsilon. Upsilon. Yeah, that's right. And so, like, specifically, upsilon here, it's a set of, come on, U1 all the way out through U sub P. I didn't make that P dimensional. My beta, as usual, is V1 through Vn. My gamma, as usual, is W1 through Wm. All right. So then my claim is that if we have beta an element of the bilinear transformations from V cross W to U, and X is, say, the sum I equals 1 to n of X upper I, V lower I, and Y is the sum J equals 1 to M, M as in mummy, of Y upper J, W lower J. So this is the setup. Then there exists constants B, I, J, upper K in the field, which is going to be the reals for us. All right, such that B of X comma Y is equal to, let me not write that down here, I want to leave that room, such that B of X comma Y is equal to the sum I equals 1 to n, sum J equals 1 to M, sum K equals 1 to P of B, I, J, upper K, and then we got ourselves a X upper I, a Y upper J, and a U lower K. Hoi. What?
He needs one more there.
One more ladder. Ah, that was a joke. Very good. I like jokes. Let's see here. So here we go. B of xy is B of the sum I equals 1 to n of X upper I, V lower I, comma, the sum J equals 1 to M of Y upper J, W lower J. But by bilinearity, we can pull both of the sums out. j equals 1 to m. Pull the constants out. And we're left with b of v lower I, w lower j. Right? But b of vi wj is an element of what? By assumption, it's an element of u, right? Which means that we can form that vector by a span of the upsilon basis. So we have that b, that, some, which tells me that b vi wj is equal to a sum k equals 1 to p of, we can say b I j k u sub k, which then I take that, right, and I just put it in here, and then I've got it. I see you guys aren't writing it down, so I'm not going to write it down either. Actually, I will write it down. So I can pull the sum out, right, because there's no k dependence, so I've got sum I equals 1 to n, sum j equals 1 to m, and I'll put that constant first, b I j upper k, x upper I, y upper j, times my, my basis. I lost my rats. I'll put it out front. I'm going to make it a different color. Sum k equals 1 to p of u sub k. There you go. Okay, so what does this theorem become? What, if u equals 2, if u is just equal to the reals, right? Then this whole discussion becomes a little bit easier, right? Then we just have b of xy is equal to a sum over I equals 1 to n, sum j equals 1 to n, m of what? Of just b I j, x upper I, y upper j, right? Because there is no, the basis for the reals is just 1, so we don't need the k. We don't need to do the sum over k. It's just 1. So this result just reduces to this if u is equal to that. In this context, let me circle back to the tensor product, right? Because notice that if we have like beta, like v upper I is an element of beta star, right? And w upper j is an element of gamma star. Where, as usual, vi of v lower j is Kronecker delta ij, right? And w j of wi is Kronecker delta ij. So the dual basis for w, the dual basis for v. If I have those, I can rewrite this as the sum I equals 1 to m n, sum j equals 1 to m of b I j, v upper I of x, w upper j of y. I will remind you of our discussion of dual spaces. We learned that the dual bases are exactly the component functions of the coordinate maps. So to pick off the ith coordinate of x, I take the ith dual vector, let it act on x, that gives me that. The jth component of y is the jth dual vector acting on y. That's the jth component of the phi sub gamma coordinate map in our language. But this is sum I equals 1 to n, sum j equals 1 to m of b, I, j, vi tensor wj acting on xy. By our definition of pointwise addition of functions. So what this shows you, this calculation that I've worked myself into the corner with, is simply the following assertion. It's that, let me erase some of this over here. Well, this, if you want, so here's a little theorem. The bilinear forms on V we can write as the span of Vi tensor Vj such that 1 less than or equal to I comma j less than or equal to n. Well, I think what I prove more directly is this. The bilinear forms from V cross W to the rails we can write as the span of Vi tensor W upper j such that 1 less than or equal to I less than or equal to n, 1 less than or equal to j less than or equal to m. See, because I just showed you that we can write B as the sum I equals 1 to n, sum j equals 1 to m of b, I, j, vi tensor wj, right? That's, if you strip off the xy acting on that, right? That's what we've shown on the other board. We've shown that this is equal to that, which is to say that these guys form a generating set for that. In fact, it's a basis. You can prove that these are linearly independent. How would you do it?
Sum them with constants and set them equal to 0.
Okay, so like maybe this. Set this equal to 0, right? Then how do I show that these are 0? Well, check this out. So if I take b of, let's say, v lower k, w lower l, what is that? So the way this works is vi gets to the vk and the wj acts on the wl by the definition of the tensor product that we wrote down. But what are those? What do you got there? Yeah, Kronecker delta, IK, Kronecker delta, JL. And as such, we squash the sum over J, we squash the sum over I, and we're just left with what? B sub K, L. Which is equal to 0, which is for some reason hilarious. I'm not sure why exactly, but some sort of, I have to put my mind in the, if I could think as the Joker, you know, some sort of purple-hatted evil villain. That's what I need to do. But actually, does the Joker? Oh, I'm just talking about Legacy Batman, aren't I? Like, when is the last time the Joker wore a purple hat? I have not seen the most recent Joker movie, nor do I care to. So. All right, I digress. Okay, back to work here. So so what we've just shown is that this is equal to 0 for arbitrary coefficient. Therefore, this is in fact, the set of such things is in fact a basis, right? So the dimension, this, you know, you can count what's the dimension of the bilinear forms? Well, the dimension of the bilinear forms from V cross W to the reals is what? It's the dimension of V times the dimension of W. M times N. Right. And this calculation also shows you how we calculate these components, right? To calculate the ijth component, you simply evaluate the bilinear form on the, you know, ith and jth basis vector of V and W respective. All right. So I'm not quite following my notes. I've injected the tensor product stuff earlier because I wanted to get to the point faster about it. Hope you can forgive me. Proposition 10.36 actually we've already proved, but not entirely. Let me point out that so what proposition 10.36 is, it introduces the idea that to each bilinear form, we can associate a matrix, right? So here we go. So if we've got proposition 10.3.6, we have B. Wow. I could try to yell back, but they don't hear it. I don't have that volume. So if we have this, and still using the notation that we used on the far board over there, right? We have B of x comma y is equal to the sum I equals 1 to n, sum j equals 1 to m of x upper I, y upper j, bij if you like. You can write these in any order you like. They're just numbers. Okay? They're scalars. But we could also write this as the matrix product, the transpose of the coordinate vector of x with respect to beta times m times the coordinate vector of y with respect to gamma, right? I thought I introduced some notation here at some point. I do not introduce notation. I guess I need to, like, the thing is I've already defined a meaning for brackets with some bases, right? But this would be the matrix of B with respect to beta for V and gamma for W, right? And all right, so I can be a little bit more specific here. Mij is equal to Bij. See, if you take this formula up here and you write it, look at what you have. You've got, so we have xi, bij, yj. So I guess I'm just, the question is, do you guys remember if we have like, A times X, a matrix A times a column vector X, how did that work? Remember? If you calculate the, like the ith component of that, I think it was the sum over, let's say, k equals 1 to whatever, n, I guess, of A, I, k, in my current notation, x upper k. And maybe I should have done a y here to make it more helpful, There. Almost there. So if the column index gets summed against the column that you're multiplying against. I need to make some notes. Like when I do my stand-up routine, I'm going to bring it back because this is killing it. So all my jokes are going to be based on whatever I'm doing right here because there's something very funny. But I don't know what it is. I'm going to figure it out though. So anyway, the point is that we can look at this as the matrix times the column vector, and then you have the ith. You've got the ith component of that multiplied against xi. It's exactly this product. If I define the ijth component of the matrix to be bij, that's it. All right. So you can contrast this. Well, actually, let me just get to the point here. There's no earthly way I'm able to write all this out. I was debating whether or not to talk about coordinate change today. I think we've reached the point in the discussion where it's natural to talk about the coordinate change issue here. So I should probably do it. Did he hand back a test today or something? Is that what it is? I don't know. They did something. I think it's abstract, isn't it? Yeah. They already got it back. Man, I've lost track of my. So the point I'm trying to get to eventually is that the coordinate change property for the bilinear form that we just defined is different than the coordinate change property for, say, a linear transformation from V to W. So the way that the matrix, so that we defined the matrix for a linear transformation from V to W before, right? We again have something that's involving, it's involving a vector space V and a vector space W and the bases between both, right? And we've just defined a matrix. This begs the question, is this the same matrix we already defined for a linear transformation? How do these two things play together? Do they? What's the deal? And the deal is that the interaction of this matrix we've just defined and the basis is, the double scrolling. Got me again. Curse you, double scrolling. Curse you. Boop, nope. All right, so see if I can explain this. All right. So for a bilinear form, we can induce it from a corresponding bilinear form on Fn cross Fm, which is just matrix. That's my example 1. We just had a matrix, so like an n vector transpose times the matrix times an m vector. That gave us the bilinear form, right? So you give me an m by n matrix, I give you a bilinear form. My point is that you can take the bilinear form on the abstract vector space, and you can build it from a corresponding bilinear form from Fm to Fn. Well, Fn and across Fm. So what I do is I define, I think that's a tilde, b tilde, which is b composed with like phi beta inverse and phi gamma inverse. That gives me a mapping from here to here. And specifically, the way this works is like b tilde of x coordinate vector and y coordinate vector of x and y respective is just equal to x transpose my, which is, so we're trying to understand how this matrix behaves with respect to the choice of the bases beta and gamma, all right? So I've got this formula that relates B to my coordinate maps. And of course I can also do this with respect to, say, beta bar and gamma bar. I can define an m bar in the same way, right? But the thing is, these are just two different descriptions of the same bilinear map, so these two have to be equal, all right? These two have to be equal, and these being equal gives me this equation right here. So if I look at the matrix with respect to the barred bases, and if I look at the matrix with respect to the unbarred bases, these should be equal. I probably should have just written this down on the board and not even gotten this thing out. That would have been simpler, right? Like, you don't have to do all of this. I think this is interesting. If you don't, that's fine. The point is, we should all understand that if we can build, B by x transpose my with respect to one choice of basis, if we choose a barred basis, we get the same equation with an m bar in the middle. The question is, how is m and m bar related? Okay, how are these related, right? So set them equal, and I solve for m as, p transpose m bar q, where p apparently is what? Well, I'm about to tell you. And there you go, Violet. You can tell me about that one. No, you want to. Admit it. So here, P is in fact the, goodness gracious. I claim that P is in fact the P beta beta bar that we talked about before. It's the coordinate map of this thing. And where was it? All right, so this is the transformation from the matrix of the bilinear form in the barred bases to the matrix in the unbarred bases, all right? So I really should solve this for m bar just to be clear, more clear anyway. So I've got m bar is pm, oh there it is, rats. It's right there, I just didn't see it. P transpose inverse M Q inverse, right? In contrast, notice that the matrix of T with respect to the beta bar gamma bar matrix is equal to P times the matrix of, well, excuse me, it's, yeah. So P gamma gamma, I think is the Q. And I probably just need to scroll down, and I have this formula next, but come on. There we go. So this is the difference. This is how the matrix of a transformation from V to W transforms, whereas this is how the matrix of a bilinear form transforms. They're quite different, right? This bothered me a lot when I was an undergraduate because some people, when people don't quite understand the math, they just start saying things like, yeah, a tensor is just a matrix. A tensor is just a matrix. That's very unhelpful because there are different kinds of tensors. And as long as they're involving two inputs, yes, they all correspond to a matrix. but they correspond to a matrix in very different ways with respect to the choice of the basis on the vector spaces. So if we study coordinate change, this and this are very different behaviors. And so the rules for simplifying a bilinear form are different than the rules for simplifying a linear transformation because of this. All right? But anyway, so like next time, we will talk about quadratic forms in a little bit more abstraction, and hopefully we'll get to what you talked about, Josh, which is the inner product. And so we're gonna generalize the concept of inner product a bit in here to something called a geometry. So we'll look at a metric as opposed to an inner product, which we're gonna lose that positive definite, that insistence that xx equal to 0 implies x equal to 0. We're gonna lose that. So anyway, thanks guys.